Today we will be talking about parsing. In particular, top-down parsing. First of all, let's write the grammar that we wrote last time. So the grammar for an expression in a typical programming language, that grammar that we wrote last time, is called the classic expression grammar. Classic expression grammar. And the classic expression grammar that we wrote last time is expression plus. Yeah, it looks like I will not have enough. I'm going to write it here. So the classic expression grammar is expression plus term, or expression minus term, or term. So why did we do it this way? Why did we introduce the notion of a term in the grammar? Yes?
Operator precedence.
Yes, exactly. To account for operator precedence, so that we put so that we give multiplication and division higher precedence than addition and subtraction. Then a term is a term times factor, or term divided by factor, or factor, where the factor is what? Identifier, or number, or expression between parentheses. Okay, so this is what we call the classic expression grammar. And last time we started talking about parsing. So what do we mean by parsing? Given what we have presented last time, what do we mean by parsing? What does parsing mean? Dividing the input into tokens, that's scanning, right? But parsing is checking the syntax of a program given based on a certain grammar that defines the syntax. So this is a grammar that defines the syntax of an expression. So checking a given program, which is a string of symbols, checking that against the grammar, or trying to match it with the grammar, or trying to find a derivation. So parsing is about trying to find a derivation. Find a derivation for a given string. So now again, your program is going to be a string. From parsing point of view, we look at your program, as a string, no matter how long, no matter how many lines of code there are in this program. It's just a string of symbols, and we are trying to match this string of symbols, or trying to check if this string of symbols belongs to the language that is defined by a certain grammar. So here in this case, we're only looking at expressions. So here, for the time being, we're looking at a program that consists only of expressions. It only has expressions, which is one of the important, the most fundamental constructs in a program, an expression. Later on, we will see how we extend this. In fact, last time we talked a little bit about extending or looking at a grammar for an assignment, for example, and the grammar for a statement. We will do more of that later, but for now we focus on the expression. So basically the parsing problem is given a string and a grammar, see if you can find a derivation for this string. So let's look at this string. A plus B minus C. Now, of course, we can come up with a derivation manually for this, right? So we can do the matching, manually. We look at this string, and we look at this grammar, and then we can find the derivation. So the derivation is gonna, we start at the start symbol expression. Then we'll have to pick one of these substitutions, right? One of these rules or productions or alternatives, either expression plus term. We expand an expression into either expression plus term, expression minus term, or term. And parsing is about selecting the right option. What's the right option? Now, by inspection here, what's the right option for this? Yeah, how did you know that it's expression minus term?
Because it's on the right, the minus.
Okay, so I guess the way you determine that it's expression minus term, the substitution at the top level is going to be expression minus term, not expression plus term, is that you looked at this, said, okay, can I look at this as, can I do expression plus term? So can I consider this an expression and then consider this a term? Will this work? No, it will not work because this is not a term. This is two terms, right? So you did this kind of attempt in your mind, and then you couldn't do it with expression plus term because this is not a term. So you said, okay, then expression minus term is going to be the right substitution because I can think of this as an expression, and I can think of this as a term. So you tried something, right? Now this is like a trial and error, and you did it in your mind, and you did it very quickly. Why? Why could you do it quickly? Yeah, you can see everything, and everything is like, how many symbols? 4, 5? 5 symbols. So this is too small, too short. A very small string. So you could do this for a small string, and you figured out the right substitution. But this is not what we're looking for. We're looking for an algorithm. We are looking for a systematic procedure, a step-by-step procedure that can handle an arbitrarily long string and that can determine the right substitution or the right production to use deterministically and without having to look ahead too far. So in fact, in this case, in order to figure this out, you looked ahead, at least you reached the minus. In fact, you looked at the whole thing in order to determine this. So what you did to get this figured out by inspection or manually, you looked at all 5 symbols. So you did like a 5 symbol look ahead, sorry. And in fact, for an actual compiler, this is 5 is too many. So we are interested in a parsing algorithm that will that can make decisions, that can decide the right substitution, the right production to use with minimum look ahead. And in fact, today we will study an algorithm that can do this with only 1 symbol look ahead, only 1 symbol of look ahead. Okay, so how? So again, we need to do this systematically. So, well, maybe what we should first try is an algorithm that will try everything. So, an algorithm will look at expression, and I need an expansion for expression. So I have these 3 options. So I'm going to look at this, consider this option first. So I'm going to do expression plus term. But of course, with expression plus term, this is not going to lead to a right derivation, as we know. So at some point, this is going to fail. Now, the point is, if I keep doing this systematically, and if I do leftmost derivation, and in order to be systematic, you have to stick to either leftmost derivation or rightmost derivation. So if in this case we stick to leftmost derivation, we consistently do leftmost derivation, then now I need to look for a substitution for this expression, right? And then if I continue to do this systematically, what will I substitute for expression? Now, think systematically. So we substituted expression plus term. So we consider the first option. So think of this as a function. You're writing a function that does this. So it will always look into the first production. So it's going to do expression plus term again. Then it will look for a substitution for expression again. And it will do expression plus term again. So the point here is that if you do leftmost derivation and your grammar has what? You will have a problem. So what's the characteristic in the grammar that led to this problem with leftmost derivation? What led to this problem? Why did we find ourselves in this infinite loop? Yeah.
Recursion.
Yeah, because of recursion. And what kind of recursion? Yeah, it's left recursion. So what put us in this infinite loop is the fact that this grammar is left recursive, and we are doing leftmost derivation systematically. Emphasize systematically. We're looking for something systematic. We know, all of you know how to derive this manually. Right? So how to find the derivation for this manual. But we're looking for a systematic procedure that can process millions of lines of code. OK, so the point is, with leftmost derivation and a grammar with left recursion, you will find yourself in an infinite loop. So the conclusion is left recursion doesn't work with leftmost derivation. But we're still interested in leftmost derivation. So later in this lecture, we'll see how we can easily convert left recursion into right recursion. You can always convert left recursion into right recursion. But let's now say, OK, we figured out a solution and to get out of this infinite loop. And then we figured out to try other options, like here for expression, we try term. Of course, this is not going to lead to anything. But thinking how this can be done systematically, you will have to try all options. At each level, you have to try all options. And if you fail, like here, term, you will not find, OK, term, I can substitute for term a factor, and a factor I can try identifier. So I can match this identifier with the A. OK. Yeah, but then what? Then I can match the plus with a term, but this thing is not going to match with a term. So here I will backtrack at some point. So if you want to try all options, if you try all options, you will have to have some kind of backtracking, right? So you tried something like this. At the end, you will realize that expression plus term, the very first substitution, was not right, and I need to try something else. So after trying all possible derivations that are based on expression plus term, you come to the conclusion that none of them works. So you will now change this substitution and figure out, OK, I need to do expression minus term. OK. So what's the point here? The point is that if you have multiple options, and that will result in a decision tree. So this is your tree. This is the root of your tree. And if you have multiple decisions to make, and then after each decision you have multiple decisions to make, this will result in a tree, in a decision tree. Now, the problem with the decision tree is that what's the mathematical relation between the height of a tree and the number of nodes in a tree? It's exponential. So the relation between the number of nodes in a tree and the height of a tree is exponential. And exponential is extremely slow unless the size of the input is small enough. Okay? So now this doesn't work. So we need something that will deterministically, or that will determine at each point what the right substitution is. And hopefully, we would like to have only one option. Now, for this grammar, or for this kind of grammars, it turns out that we can come up with a parsing algorithm in which there is only one option at each point. There will never be any point at which there are multiple options. There is only one option. If we just get rid of the left recursion and convert it into right recursion. Okay. So let's now learn how to convert left recursion into right recursion. Then we will see how this trick can help us parse this or parse that expression, parse that string x a. What was it? It was a plus b minus c. Okay. In fact, I'm going to use a different string. I'm going to use this string, a plus 5 times b. Okay. So now, left recursion and right recursion. So let's look at this general. If you have something like x is x alpha or beta. Of course, with recursion, you'll have to have a base. Now, if you try to do the derivation from this left recursive rule, you will see, okay, x, I'm going to do x alpha. You keep doing x alpha, and at the end, to end this derivation, what will you have to have?
Beta.
There will be a beta. So how can you describe the string that is derived from this? A string that is derived from this grammar with this left recursion is what? It always starts with beta, then followed by any number of alphas, right? So that's what we want. Start with beta and followed by any number of alphas. Now this is expressing this, starting with beta, followed by any number of alphas. This is something that we can easily do using right recursion instead of left recursion. So that's what I want. X, I want to start with a beta, then followed by something that will give me any number of alphas, right? So I'm going to call that thing x prime, and then x prime is going to give me any number of alphas, and I can do it with right recursion, right, instead of left recursion now. So what's the right recursion? So it's just alpha x prime, or what? Epsilon. So this grammar is equivalent to this grammar. Both of them generate a beta followed by any number of alphas, and they are equivalent. But this is left recursive and this is right recursive. So this is left recursive and this is right recursive. As we will see later in a few minutes, the right recursive form is going to work very well with the kind of parsing that we will be studying today. So now let's generalize this, because this is not general enough. Now what about this more general form? X is alpha 1x or alpha 2x or alpha nx or beta. So generalize. What would be the right recursive equivalent of this? X goes to, what's, generalize this. So it will still start with beta. So it's still beta x prime, but my x prime is what? Is alpha 1 x prime or alpha 2 x prime or alpha n x prime or epsilon. So this is a generalization. So basically you don't have to have one left recursive rule. You can have multiple. Oh, sorry. So this is not left recursive. So it's my fault. Okay. So it's, I wrote them right recursive. Sorry, my fault. Okay. So this is x alpha 1, x alpha 2, x alpha n. Sorry. So this is the left recursive. So this is left recursive, multiple left recursive rules, and this is the right recursive equivalent. Okay. Now, let's apply it to this grammar. Now, to apply it to this grammar, let's now forget about this. Let's look at the general rule. Let's look at this. What's my x? Expression, right? Expression is my x. So this is my x. This is an x. Okay. And what's the term? Yeah, look at this. Match it with this. Match it with this. So what's the term? Alpha or beta? This term. Yeah, the base. This is the base. So this is the beta. Now where is my alpha 1? Yeah, my alpha 1 is plus term. So this alpha 1 is not necessarily a single symbol. In fact, it can be anything, any a combination of terminals and non-terminals. Okay, so this alpha here can be anything. Doesn't have to be one terminal. It can be any combination of terminals and non-terminals. So this is my alpha 1. This is my alpha 2. Now, using this, what will I get? Expression is what? Beta. What's beta? What's beta? Term. Expression prime. Where expression prime is what? Where is alpha 1? What's alpha 1? Plus term. So alpha 1 is plus term expression prime or minus term expression prime or epsilon. So we're matching with this. So we have two alphas here. Now same thing for that term. So here, where is the beta? Where is x? X is term. So this is the x. Where is the beta? Factor. And this is alpha 1. And this is alpha 2. So now term is what? Beta. What's beta? Factor. Term prime. Where term prime is alpha 1, which is times factor term prime or divided by factor term prime or epsilon. Now what about the last grammar or the last three productions for defining factor? Do I have recursion? No, I don't have any recursion. In fact, I have indirect recursion here, but that's another story. I don't have any direct recursion on factor. So I'm not recursing on factor here. So there is no recursion. So this is just stays as is. So this just stays as factor is identifier or number or expression. Okay. Now, any questions on how we converted this left recursive grammar into this right recursive grammar? So this is left recursive, and this is right recursive. Now, does this right recursive grammar look odd or unnatural? Does it look unnatural or counterintuitive? Yeah, so clearly, this is the grammar that's intuitive and logical and human readable. So this is not the grammar this is the grammar that you would construct as a human being, but this is a grammar that we got by converting this left recursive grammar into a right recursive grammar. So this, plus term thing and minus term thing looks very awkward, right? Yeah. So, well, this is this is part of the procedure, but we'll see that this is going to be very powerful. In fact, there is a the parsing algorithm that we are about to describe is called LL1 parsing. It's a top-down parsing algorithm in the sense that it starts from the start symbol. By the way, in this course, we will cover only top-down parsing. So we will not cover bottom-up parsing in this course. We'll only cover top-down parsing. And LL1 parsing is one top-down algorithm where L, what do you think the L stands for? Well, we have two L's, in fact. Can you make a guess? Well, in fact, it's not leftmost derivation, right? So the first L, this L means we scan the string from left to right. We scan the string from left to right. Okay, and the other L, this L, it means leftmost derivation. So we do a leftmost derivation, we scan the string from left to right, and what do you think the 1 is? Based on what we have said. So it's the number of symbols of look ahead. So the 1 is one symbol of look ahead. So we only need one symbol of look ahead. And based on one symbol, we will be able to determine which substitution or which production will be used. So let's try it on this. So let's try it. I don't think we need it. So we will try it on A here. Let's put it here. A plus 5 times B And after this, I have a, I need some kind of symbol to indicate the end of the string. So we will use end of file. Some books use the $, but we will use end of file to mark the end of this. And initially, we are processing this string from left to right, so our pointer is pointing at the A. Now this is something that's coming from, this have been scanned, and the scanner just identified this as an identifier, and this is a plus, and this is a number, and this is a multiply, and this is another identifier. So this has been scanned. Okay, so now let's try to do a derivation. Of course, with the right recursive form. So we start, it's a top-down parsing algorithm, so we start at the expression. How many possible substitutions do we have? 1. So we have no choice. That's easy, right? So we only have one possible definition. So it's term expression prime. Good. So now this is the leftmost derivation. So we should look for some substitution for term or expression prime. Term, because it's leftmost. So for term, how many options do we have? Only one option. So far we didn't have to choose. So it's just factor term prime. We didn't have to make any decisions. Now we need to find a substitution or an expansion for factor. Now for factor, we have 3 options: multiply factor, divide factor, and epsilon. Now, which one should we choose? I'm looking at the wrong. So for factor, it's identifier, number, or parentheses expression. Why identifier?
Because A is on the pronoun.
Yeah, exactly. Because the next symbol in the string is an identifier. So we have 3 options: identifier, one that starts with identifier, one that starts with number, and one that starts with open parentheses. And clearly, we have an identifier. We don't have a number. We don't have open parentheses. So this is the only right choice if this string is indeed a valid string that belongs to the language. So there is only one correct substitution or one correct production that we can use. So this factor must be an identifier. Now, since we have already matched this, we advance our pointer. We have already matched this identifier, the A. So we advance our pointer, and now we are looking at what? The plus. Okay? All right. So now what's the next step? Find an expansion for term prime based on the next look ahead. So for term prime, I have multiply, something that starts with multiply. Do I have a multiply? No. Something that starts with divide. Do I have a divide? No. So the only option that I have is epsilon. So I just put an epsilon. So it's like I skip. Why? Because I don't have a multiply and I don't have a divide. What I'm seeing in the input is a plus. Okay. Now for expression prime, I have 3 options. One that starts with plus, one that starts with minus. Now this one that starts with minus is clearly right or wrong? Wrong. So this is clearly wrong because it starts with minus and I'm seeing a plus. Now this is correct. But in fact, the epsilon can potentially be correct. In this case, it's not correct. But in some cases, the epsilon may be correct. Why do you think that's the case? Why would... Now, this is not true in this case. But in general, in a situation like this, the epsilon may be valid, may be a valid option. Why would the epsilon be a valid option even though I'm seeing a plus? Because it could be that the symbol that I'm trying to find a substitution for, I can substitute epsilon for it. And then this plus is for something that comes after the current symbol. So here, there is nothing after expression prime. So this is not going to be the case because there is nothing after expression prime. But suppose that after expression prime, I had something like A, and this A may start with a plus. Now, if after expression prime you have an A that may start with a plus, in this case, I will have two possible substitutions for the expression prime. The first substitution is this. So I consider the plus to be part of the expression prime. Or I can substitute epsilon for expression prime. And then this A, this plus, belongs to this hypothetical A. But here, I don't have this hypothetical A. Now, I'm bringing this up because in general, you may have grammars in which the epsilon may be a valid option. Now, what will determine if the epsilon is a valid option or not? Looking at what the next variable can start with, or in fact, looking at what can follow the expression prime. So we will need to find what we call the first and follow sets. The first set and the follow set for each variable in the grammar. So first and follow is something that we will be covering next time. Okay. So first and follow set will be covered in the next lecture. For now, so let's go back to what we have. In fact, given that expression prime cannot be followed by a plus, this is the only valid substitution, and I just put plus term expression prime. Expression prime. Now, what should I do next? Now, I have consumed the plus. I have matched it. So I advance my pointer. So I have matched the plus. Now I need a substitution for term. For term, I have factor term prime. Only one option. And for factor, what are the options? Identifier, number, open parentheses. Which one? Number. That's what I have. So the only right choice is a number. Okay, and this number is the 5. And since I have matched the 5, I advance the pointer. Now I'm looking at the multiply. Now for a term prime, I have something that starts with multiply, divide, and epsilon. Again, the epsilon, I have to do some further analysis to determine if the epsilon is valid or not. But in this case, it's not valid. So it's the multiply. So I have multiply, factor, term prime. And since I have recognized the multiply, I advance the pointer, and now I'm looking at the B. Now for a factor, what's the right substitution for a factor based on what? Identifier. And this identifier is the B. And I advance my pointer. So now I'm looking at the end of the string. Okay. Now what remains? Term prime. So I'm not seeing a multiply or a divide. The only right substitution, epsilon. And for expression prime, I'm not seeing a plus or a minus. The only right substitution is the epsilon. Okay. So I found a derivation for this string. And at each step, there was only one correct choice, right? Except for, sometimes, the epsilon may have been a valid choice. We'll say more about this epsilon and why or why not it's a valid choice next time. But are there any questions about this derivation for now? Okay, so this is the LL1 parsing technique.